Calculating inductors in AC. This presentation, we are going to be looking at how we calculate inductors in alternating current circuits, but we're also going to be looking at what the differences are between a DC circuit and an AC circuit with the same component. So let's take a look at a circuit with an inductor in it. I've got this great little simulation set up. It is from the University of Colorado Physics Department, and you can download these free by doing a really quick and easy search for University of Colorado Physics simulations, and you can run them straight from their website. So this is an inductor right here. We've got a switch. And then we've got a DC and an AC source. So the first thing is I'm going to connect in the DC source so you can see how that operates within the circuit. And we've seen this a few times before already, but I'm just going to use it as an example. I have no resistor in the circuit. All I have is an inductor. So I'm going to close the switch. And the current starts very slow. And now what's happening? It's getting faster and faster. And it's getting faster. And oh my goodness, I've just set the entire simulation on fire. And the reason for that is because the counter EMF gets less and less and less. So essentially what's going to happen here is the current is going to continue to increase in value unless I had a resistor. Because really, what's the resistance of this inductor? Well, it's just the resistance of the wire. So it could be like 0.01 ohms, which means there's a lot of current that could potentially flow. Whew, let's put out that fire, shall we? So now, let's take the exact same inductor, and instead of a DC source, let's put an AC source in. Now, the inductor is still going to want to oppose a change in current flow, but when we put an AC source on, the flow of current will be in one direction and then another, and it will happen so quickly. It'll be 60 times a second on a real system. This one, the frequency is only going to be about half a hertz, but that's only so that we can see visually what's going to happen. So there's my AC source. It's the same voltage as my DC source. They're both 75 volts. Let's close the switch. No short circuit happening here. And it's kind of difficult to see with a simulation because of all the different properties that are interacting together. But what ends up happening is the inductor has counter EMF that's opposing this change in current flow direction 60 times a second on a typical AC system. And so it does like this shifting back and forth because it's an AC circuit. And it will start to shift more into the upward direction or counterclockwise given enough time. So what I want you to realize is that this is offering some form of an opposition to current flow, which sounds very similar to what we have with resistance, which is an opposition to current flow. So let's go back to our sheet of paper here and see what we have for calculating values. So when we calculate inductors in AC, we still have the same properties as a DC inductor circuit in some way. So inductors, there's my inductor. Inductors are measured in henries, which is represented with an H for a measured value. Inductors themselves in an equation are always represented with an L. And then when we are in a DC circuit, we don't actually calculate any sort of resistive property, do we? In a DC circuit, this offers pretty much no opposition to current flow. All it will change is the amount of time it takes for the current to get up to its peak value. In a alternating current circuit, that effect that we saw in the animation was one of opposition to current flow. And so that effect in an AC circuit is referred to as the way in which the inductor reacts to a constantly fluctuating current. And that is referred to as inductive reactance. Inductive reactance. Inductive reactance is only found in a AC circuit, only in an AC circuit. So if it's only found in an AC circuit, we can only calculate these values when the inductor is in an AC circuit. Inductive reactance will also have a means of representing it in an equation. So this would be the symbol in equation. And it will also have a means of measurement. How do we measure the quantity of inductive reactance? And the quantity is measured in ohms. And so in an AC circuit, if I wanted to calculate the ohms of inductive reactance that this particular inductor possesses, we would use this calculation here. So XL is equal to 2 times pi times F times L. So 2 is just a constant value. It's number 2. We use it for everything on this calculation. This is pi. So on your calculator, pi depends on what calculator you have, but pi essentially is 3.14, right? And then it goes on and on and on, never repeats, blah, blah, blah. F, this would be the frequency of the circuit that we stick it into. And we know frequency is measured in hertz. And then finally L, well, we already know what L is. L represents the inductor, and that is in henries. So this is the inductance in henries. So what we have with an inductor is something that is a structural item, something that is physical, that the henries cannot be adjusted unless you physically adjust something on the inductor itself. Remember, the induction for a inductor has to do with the number of turns, the type of core, and the permeability of that core and the length of the magnetic field. When we're dealing with an AC circuit, the way in which an inductor reacts within an AC circuit, really the only thing that's going to adjust this is the frequency. So let's take an example of an inductor in an AC circuit. So let's say we have a, I don't know, 500 millihenry inductor and a 120 volt AC circuit, and it's going to be 60 hertz. Well, I can calculate the XL of this circuit, and here it is. There's my inductor connected to AC and back. So I'm going to calculate the XL. XL is equal to 2 pi F L, which is 2 times pi 3.14 times 60 times 500 millihenries. And 500 millihenries would be equal to 0.5. So I take my calculator, depends on what type you have, but sometimes there's an actual button right here that's pi, and other times you have to press second function and then find it on your calculator. Mine's depends which one you have. So 2 times pi times 60 times 0.5 equals 188.49. 188.49 what? Ohms of inductive reactance. Ohms of inductive reactance. And what that means is that we can take a formula that we have used in first level and apply it here. Remember this? It's Ohm's law, isn't it? And we always refer to it as Ohm's law. It's not resistor's law, is it? It's not the law of resistors. It's the law of ohms. The current in a circuit is equal to the voltage divided by the ohms. And so ohms, regardless if they are resistive ohms or inductive reactance ohms, can be utilized with this equation. So I is equal to E over ohms. And I suppose if you wanted to, you could sketch it this way. I is equal to E over XL, which really means the same thing. I is equal to E over ohms, which would then be 120 volt divided by 188.49. 120 divided by 188.49 gives me 0.636 amps worth of current. There's only one item in the circuit. It's an inductor. So what voltage would be across the inductor? Be a full source voltage, 120 volts. And how much current would be flowing through the inductor and through the entire circuit is 0.636 amps. Okay, so let's take the exact same inductor and let's just change the frequency. So I'm going to do 500 millihenries. 120 volt AC, but this time I'm going to convert it to two different frequencies. So the hertz is going to vary, okay? So we're going to do one circuit at 30 hertz, and we're going to do the other circuit at 60 hertz. And we're going to see what the difference is in the XL as well as the current. So first, let's calculate XL. XL is equal to 2 pi FL. And that means for our two different circuits, although they have the same inductor in them, they are going to react a little bit different within the circuit. So XL is equal to 2 times pi times 30 times 0.5. 2 times pi times 30 times 0.5. Gives me a total inductive reactance of 94.24 ohms. So that is the total XL of this particular circuit at 30 hertz. The total current value is the voltage divided by the ohms. 120 divided by 94.24 gives me 1.27 amps. On the other side, we have 60 hertz, or no, I want to change that. We started at 60 in the previous example. I want to do a lot more. Let's do 120 hertz, sorry. 120 hertz. So XL is equal to 2 times pi times 120 times 0.5. 2 times pi times 0.5 gives me 376.99 ohms. The total current then that would flow through this circuit is obviously going to change because Ohm's law will dictate 120 divided by 376.99 equaling a current value of 0.318. So what can we take away from this? What changes inductive reactance of an inductor? Well, the frequency. The frequency will change the inductive reactance of a single inductor. Will frequency change the inductance of the inductor? No, it won't. Frequency only has a change on the effect that this exhibits when connected into AC. It does not have any effect on the 500 millihenry value. Remember, 500 millihenry is a physical value and therefore needs to have a physical change to the component if you wanted to adjust it. That brings us to the end of our calculating impedance, or XL, inductive reactance.